I'm Mel.
I'm Tiff, and we're On Pump. Doug, we just want to welcome you to On Pump. We're very excited to have you here. It is a perfusion podcast, but it's also more than that. We target cardiac surgery in general and, sister professions in cardiac surgery. So it's pretty broad, but we just like to hear from all sorts of professionals like you. So why don't you give us just a little bit of a bio to get started? So welcome, Doug Vincent, to On Pump.
Oh, well, thanks, guys. It's great to be here. So I trained as a mechanical engineer. I came out of MIT in 1989 and went to work for Dean Kamen in New Hampshire as a self-made millionaire in the medical device industry. And honestly, since then, I've been doing medical devices. So unbeknownst to me, that was not just the first job, but a launch of a career.
How long have you been working on VentriFlo, your current device?
Oh, well, a while, I think is the one way to put it. The first job I had, I became systems engineer on a peritoneal dialysis machine that when we launched in 1993 came to dominate peritoneal dialysis. And even still today, it's the number one dialysis for peritoneal. And that process really got me into medical pumps. And then I worked for a company that did a lot of different laparoscopic and hysteroscopic pumps. And then I ended up at a company in the late 90s called Abiomed. I was a small company at the time, and their focus was trying to create an artificial heart. But I was most intrigued with their BVS 5000, a pulsatile pneumatic system for bridge to recovery. And the focus heading to the artificial heart, they weren't as excited as I was to eventually say, how could we take this power of the pulse and do some new things with it? So I left Abiomed and started a consulting company. And a couple of years later, I was skiing with a good friend of mine who was the director of acoustic research at Bose. And a lot that I'd learned at Abiomed had haunted me, that I really felt two things that the industry had concluded were wrong. Number one, that pulsatile flow was not important or a differentiator. And number two, even if it was too hard to manage. And so they kind of turned away from it, really for engineering reasons, not for clinically relevant reasons. And so in the early 2000s, we started to work nights and weekends on it and signed a stack of paperwork with Bose, and they had a linear motor, and which is really a subwoofer on steroids. So if you think about a rotary motor, which most blood pumps are based on, like a drill motor, they spin around, and then you somehow have to convert that into some kind of flow, either, with a tube crusher for a roller pump or an impeller for a centrifugal pump. But a speaker, of course, goes up and down in air, high frequency. But our idea was to just slow it down and use it to mechanically push and pull on a diaphragm and therefore recreate the human heartbeat outside of the body. And that's when I think our first patents were 02, 03, something like that. We're all based around that. So it's been a while.
I love that you mentioned the roller pumps. A lot of the stuff that we hear today, pulsatile perfusion. We have a few papers, a little bit of research in that in perfusion. But I think a lot of it was maybe from at least 10 years ago. And it was using roller pumps, and the setting on the devices, you had to have the pump that did that. So the S5 was one of them that had a pulsatile setting. But all it would do was ramp up and ramp down either the centrifugal or the roller pump. So a lot of places wouldn't implement it because you would get really high circuit pressures. And so you were kind of testing the limits of the upper limits of your devices. And at the same time, you were just causing changes in pressure, but not necessarily like hemodynamics. Like you're not getting true pulsatility. So can you talk a little bit about how there's a difference between those two and how, VentriFlo can actually help with cardiac patients by establishing true pulsatility?
Yeah, no, it's great question. And, I guess I would say this, that there's continuous flow, which I think people can visualize very clearly, right? Kind of a flat pressure line, but also a flat flow line. But of course, all of the body's biology is based upon pulsatile flow, and that's created by the ejection of the heart. So if you think about the left ventricle, that delivers stroke volume by stroke volume into the elastic arterial tree. It's not really a pressure source. It's really a volume source. It's a stroke volume source. And if you say, just for some easy math, if you had a 50 cc stroke volume at 100 beats a minute, that's 5 liters, right? And so you get the flow by the stroke volume and how often you do that. Now, what that looks like from a pressure perspective, there's lots of ways to recreate that pressure tracing, and I'll describe that quickly in a second. But it's really the flow that you want. You want that delivery of the stroke volume, and then a period of time where there's no volume going into the elastic arterial tree. And I'm sure I'll talk some more about that too. But the key point is this. If you think about, I'll just do a mental experiment with me. Take a bag and hold that bag. No flow goes in or out, but you squeeze that bag and relax that bag. You could do that at, say, 120 over 80 millimeters of mercury. You could make a pressure trace that looks physiologic, but there's zero flow. What we want, though, is the stroke volume delivery. And so I go through all of that to say, yes, with a roller pump, you can speed up and slow down. And the roller pump is a volume displacement device, but it's really a volume displacement device secondarily. The first thing it is a tube crusher, right? So it pushes a slug of fluid forward in between the rollers, and it counts on the springing back of the elastic tube to refill so that there can be another bolus of fluid to move forward. What VentriFlo can do is, like the native heart, we control how quickly we fill. So it's active filling, and then it's active delivering, and different sizes. Although our main focus today is on up to a 40 cc stroke volume, kind of our intermediate size. We deliver that full 40 cc's when at high stroke strength, and I'll talk more about that later, at a user-defined beat rate. So we can independently control the stroke volume versus the beat rate and deliver that hemodynamic energy, stroke volume by stroke volume, into the elastic arterial tree, again, just like the native left ventricle. And all of that's important because our elastic arterial trees is made up of cells and sensors. The sympathetic and the parasympathetic system are all signaled by what happens to that stretch and relax that we consider a pulse, and everybody knows is a pulse, but we don't think of it as flow. But that's what that pulse is. It is a volume that's being delivered into that elastic arterial tree, and then that flow is going downhill, if you will, into the capillary beds to the business end of circulation to deliver, as the red cells fold up and slide through the nutrient capillaries to drop off oxygen, pick up CO2, and make sure the nutrients get dropped off, and the metabolic waste can come back around to the rest of the organs. So where VentriFlo is fundamentally different is we are a volume displacement device, stroke volume by stroke volume at a user settable beat rate, or if you sync the ECG based on what the patient's ECG is. And so we can either counterpulse or copulse depending on what is needed in that circumstance. So very different than what a roller pump can do with a rotary motor that speeds up and slows down, and certainly than a centrifugal pump that is fundamentally decoupled from the blood. And what I mean by that is the impeller is spinning very quickly, and it kind of flings the blood as it comes in, but it's not coupled to it. Our diaphragm is fundamentally coupled 1-for-1 with the blood. And so the active fill is when we draw back the diaphragm, that brings blood into the chamber, and then we deliver forward, and that squeezes gently blood out of the chamber. That coupling allows us to have a very key feature of pressure sensitivity. So really it's as much a transducer as it is a pump. So let me take a breath there. I know I've been accused of having a liquid cooled tongue, so I can go off on this stuff. So I don't mean to just do a full rant.
No, I'm looking at some of our questions we had scripted for you, and you're rolling through them. But that's what we like. We like the, all the information coming from you. So that's good. I mean, we all know who the true heroes are, and that's the engineers in medicine. So thank you also for kind of drawing those comparisons with the other pumps on the market. So I just kind of want to go back in time and, go through like what brought you to this spot now? Like, how much work has this really been for you throughout the years? Where did you start, and how much has your invention kind of evolved over the years?
Well, the basic idea is really the same as we conceived it in the early 2000s. And that was a linear motor, mechanically coupled to a diaphragm, and then controlling the electrical waveform into that motor so that we can push and pull with different strength and different shape, again, so that we can recreate literally the human heartbeat outside of the body. That concept has been the same all along. And as simple as that is, thousands and thousands of engineering hours have gone into this by really a remarkable team that, one of the amazing things about this basic architecture of essentially a subwoofer on steroids coupled to a movable diaphragm and then one-way check valves. I haven't talked much about those, the ball valves that we selected, that it works well at small stroke volumes and all the way up to the max stroke volume, say in this what we call the mama bear size, the mid size, to 40 cc's. That just like a speaker, you can put any waveform you want in it, which is wonderful. But of course, picking that waveform and making it easy to control so that, you, the perfusionist, when you walk up to the system in very, very short order, you know what to do. You've got a knob. I'll describe the stroke strength and what that does, but that would be very analogous to, say, the speed of a centrifugal or a roller head. And you turn that knob up, that's harder that we push and harder that we fill. But all the details under the hood, to make that smooth and seamless, and to be able to work as low as 20 beats a minute and up, to 130 beats a minute, depending on either what you or ECG tells the system to do, and have that be smooth. It's enormously complex, and it's something we're very proud of, but it highlights, as simple as the concept is, and this has worked against us sometimes, by the way, but as simple as the concept is, all of those details are hard to make, simple and safe user interface. So it could be a drop-in replacement for where you would normally use a roller or centrifugal pump. But that's what we achieved. So a lot of time, a lot of energy, a lot of effort, a lot of mistakes, but we're very proud with where we are today. And, really on the cusp of being able to have tremendous impact in a number of different areas from a patient perspective, all the way we think from transplantation on one end to cardiogenic shock and ECMO patients, and then to heart surgery for, reduced acute kidney injury and that sort of thing coming out. But there's a lot there because it really is a third way. It is not a roller pump. It is not a centrifugal pump, but in many ways it has the best attributes of each. And that's taken a lot of time to develop a third way. And we would argue a technology unlike those two technologies that were designed in this century and for modern patients. I know I covered a lot, and I'm happy to talk more, but I figured I'll let you ask a question or two.
Oh, sometimes with Mel and I both on, we kind of give each other a little pause for, who wants to go first and chomp at the bit. But I guess you kind of covered, there are different stroke volumes. I mean, how low can you set that to? I mean, in terms of the pediatric patient, will this work for the pediatric patient?
Yeah, it's a great question. We originally imagine that there would be 3 blood pump sizes. Again, baby bear, mama bear, papa bear. So we said, let's start in the middle for a lot of reasons. We'll work out the issues and then we can scale down as well as scale up. What we've been delighted with is that this quote unquote mid-size has a higher end that we didn't expect and has a lower end that also surprised us. So we originally designed this for, thinking it would need to be about 800 mLs per minute to about 3 liters a minute. But partly because of this architecture, that when we put in current to our motor and we say, for instance, push on the diaphragm, and that tries to deliver volume through an oxygenator and through a cannula, the size of that oxygenator and the size of that cannula really dictate how quickly that volume comes out. And so let's say we didn't have any oxygenator or cannula on there and just had 3/8 inch tubing into, say, a reservoir that mimics the elastic arterial tree, what we call the Windkessel bag. We do over 6 liters a minute in that. And on the other end, if you put a very high restriction, say a 50 gauge needle, we can go down to as small a stroke volume as 1 or 2 cc's. Now there's dead volume associated with that doesn't really buy you anything. And you have some concerns about turnover and washout. But what we've seen, and I'll tell you about an experiment that Dr. Bartlett invited us to do a year ago. What we've seen is surprisingly good thromboresistance and washout of the valves and of the valve body all the way down to a 2 cc stroke volume. And so specifically, it was at ELSO 2 years ago, I was talking with Dr. Bartlett and his team, and he kind of asked the same question. Well, how low can you go, and how resistant are you to forming clots or thrombus in, say, a VV ECMO on a sheep? And we said, well, we don't know. We've always done everything with, 350, 400 or above, for ACT. And so he said, well, come on out to Ann Arbor. And he was kind enough to gift us an animal. And we set up to run VV ECMO on a fairly large sheep. And the goal was to run the first 8 hours with after cannulation. We used anticoagulant heparin for cannulation, but once we were on pump, there was no additional anticoagulation added. So we ran the first 8 hours at 1,000 mLs a minute, and that was at 50 beats. And so if you do the quick math there, that was saying we had a 20 cc stroke volume 50 times a minute. And that was going through a baby FX05 Terumo Capiox oxygenator, and no problems. So then we said, okay, let's cut that in half. So we dropped down to 500 mLs a minute for the next 8 hours. And that was down to a 10 cc stroke volume, which is really our low end limit. And it ran for another 8 hours. And again, the only thing keeping the entire circuit, the valves, the pump, the oxygenator, the cannula from clotting was the pulsatile flow. And then when we shifted to 100 mLs a minute, that was a 2 cc stroke volume. We only lasted 2 hours. And then the circuit started to clot. And once it started to clot, it clotted very quickly. And I don't know what went first, the oxygenator, the cannula, because by the time we could get to it, everything was just, jello. But one of the great things about pulsatile flow in low or no anticoagulation settings is because we do all of the flow in half of the time, that's rough numbers, and our peaks are roughly 3 times. So at 1,000 mLs a minute, our peak is really 3 liters a minute. And of course, half the time it's not flowing at all. So how we ramp up and how we come down, and then how the ball valves work. Well, people may be surprised we chose ball valves, and I'll talk more about why. One of the key benefits that highlighted was for them to close, there's a little bit of backflow. And so all around the balls, all the time, every stroke, there's flow. And so that whole architecture of building volume, delivering volume beat by beat allows us to not have a constant vacuum sucking, not have a constant pressure pushing, but it happens beat by beat. And there's a little bit of backflow that keeps both those ball valves moving. That inefficiency actually helps minimize any stasis spots and allows for turnover in the chamber. So that's a long answer to your question, but architecturally, regardless of what your beliefs are, I guess, of how we became, Homo sapiens, there really are some incredible architectural benefits to pulsatile flow just physiologically. And that element of movement and back movement, how valves close and what the peak flows are in between, and as the elastic arterial tree stretches and then relax, all those things factor into what helps maintain proper, helps the blood know when to be liquid and when to be solid, which is really an amazing thing when you think about it, right? And some research, you probably are familiar with this, that I just find fascinating on, von Willebrand's, the chains on the endothelial cells and what happens in pulsatile flow. And what we can see now, researchers can see that it unfurls during the max flow, but in that period when the heart is refilling, it coils back up and it protects it and it keeps it from being cleaved by the Adams 13. So there's, it's just, everything works together. Again, I go back to Jack Copeland, and his, take it like an engineer, take it back to first principles engineering. In his case, first principle, clinical understanding, biology. All of the body's biology is based upon pulsatile flow. And everywhere you look, you can see where there are attributes that are frankly marvelous in how the body is tuned for that volumetric delivery, and that it happens all the time. And so we think of it as pressure, but really it's stroke volume by stroke volume. Everything happens in the body beat by beat. And that's what we've tried to recreate. And what's new about VentriFlo is we're able to do that through typical oxygenators and typical cannulas and typical tubing, all that was designed for continuous flow. And when we started, we weren't sure how well it would work for this, but it turns out I think because a lot of the biological elements of it actually works surprisingly well.
That's it. I love that you brought up the von Willebrand's factor. I was actually going to ask you about that. Like, if you had done any kind of like preliminary studies on how VentriFlo and its true pulsatility, like if you had preservation of coagulation factors, better than those laminar flow devices.
Yeah. So what I will say, Mel, is it's very early days on that stuff. And, thanks to Dr. Bartlett and his wonderful lab, we have some insights into that. When I talk about the von Willebrands, there's some folks down at UAB that are doing some work on pulsatility that we've worked with in collaboration, but many others not affiliated or doing any collaboration yet with VentriFlo, but have really come to try to tease out, endothelial cell function, what happens to the parasites as they control the red cells, as they flow through the circulatory bed, and a lot of what happens when you lose that pulsatility. And this part is, I think, amazing. And a number of independent researchers doing with different ways to try to create pulsatile flow and manage that, and different techniques to look at it. What they've all come to see is that when you lose natural physiologic pulse into the elastic arterial tree, is something like 20 to 30% of the distal capillary beds throughout the bodies, kidney, lung, brain, and gut, they start to drop out. And so that part of the tissue is being starved. But, and this is the incredible thing, the same number of red cells are going across, in general, each of those capillary beds. And so how that can happen if 20 to 30% of the nutrient capillaries are dropping out is the arteriovenal shunts are opening up. And so then the velocity of the red cells in those AV shunts is much faster. So the same number of red cells per second or per beat, however you want to measure it, are going across that, but they become very, very heterogeneous. So it's not getting good distribution. And when that happens, it's like up to a third of the body that's holding its breath while on continuous flow. And that's what happens. That's how continuous flow, the longer you're on it, it can foul all the sympathetic, the parasympathetic, as well as the neural hormonal secretions, nitric oxide, and so forth. Because if you think about what continuous flow does to the elastic arterial tree, it takes and stretches and holds it, which ironically, at holding it out like a balloon that's stretched, that's where the endothelial cells don't know what's going on. The von Willebrand chains that are hanging off of them are stretched out, and now they're exposed and they can be cleaved, and all the other bad things that happen with that. But the nitric oxide release and all of the signaling that is built around that rhythmic pulsatility gets fouled. Now, what's amazing, and this is amazing about the human body, is that there are compensatory mechanisms at the system, the regional, and the local level that in most patients, they can compensate for a while. So, we've come to view continuous flow, and I think there's 50, 60 years proving this. Continuous flow is much, much, much better than no flow at all. But it's only a 70% solution. If you really, and you can survive on it, but if you really want to thrive and utilize all of the mechanisms in the biological organism that we're based around pulsatile flow, you need that pulse.
This is so interesting. I mean, my brain is kind of going off like fireworks. First of all, I've read a couple papers recently on some institutions that titrate in nitric oxide in their ECMO system, and they find that it helps with the overall anticoagulation. It helps reduce clotting on the interface of the oxygenator. And so I can only imagine that with, given the nature of pulsatile flow, you won't need those, you won't have to compensate in those ways on ECMO. So that's a really great benefit of VentriFlo. But then,
so sorry to interrupt, Tiffany. I mean, the thing that we'll have to see, and I want to be clear here that I clearly believe in the power of the pulse, that it's not a silver bullet. It doesn't solve everything.
Right.
But what I would say, and to those points, is we're very comfortable with adding chemical or pharmaceutical energy to our bloodstream.
Mm-hmm.
What we've overlooked is adding the hydraulic or mechanical energy to the bloodstream in the form of pulse. The reason I say pulse is, like a lot of things in medicine, it's dose and delivery dependent. And so, Mel, when you were talking about the roller pumps or the centrifugal pumps, it's the right idea. It's just not the right dose, and it's not the right delivery because of what you're really trying to get happen is that stretch and relax of the trunk, the elastic arterial tree, and all of the good things that happen with that in the nervous system and for the neural hormonal secretions. And unless you activate it, really from the womb on, you can't expect all of the other things that can be helpful to happen. Now, all that said, anytime, and you know this better than I because you practice it every day, anytime you hang an extracorporeal circuit off of an organism, off of a human, it's a highly pathologic state. I mean, there's lots of stuff that happens. But from our perspective, we're trying to make one thing less pathologic, and that's by not having continuous flow, which we were not, it's not a natural thing at all. And it's not just I don't want to say, because it feels good, but when you look into the mechanisms, it is fundamental to how the body's biology is constructed.
Well, it's interesting I can only speak from the adult practice. I don't really do pediatric bypass. We cover pediatric ECMO, but from an adult perspective, it's always been interesting to me that, let's take a centrifugal head, for example. and you're on bypass and if your map starts to decrease, a lot of people will try to increase flow to try to get like a response hemodynamically before having to go to vasopressors. But I always have this conversation with new grads, and I don't know if maybe I'm missing something. So feel free to correct me if I'm wrong, but it just seems that if you start jetting flow through a cannula, you do have that Reynolds threshold, right? So like you do have that threshold number where you're going from something that's atraumatic less traumatic to the patient to becoming very traumatic. And you start hitting a certain velocity of blood flow into the endothelial layer of that arterial tree. And you're going to start creating like fissions within the endothelial layer. So you're going to kind of have your coagulation system go out of whack. You're going to cause some damage to the inside of that vessel. Whether or not it's significant is another question. But at the same time, you're also priming those baroreceptors to stop responding because you're jetting so much velocity into it that all it's going to do is start to relax. And then you almost have a refractory SVR issue that you're precipitating upon the patient rather than fixing the issue.
Yeah. Well, I mean, you get at really, from my perspective, a lot of the complexities, and some I think I have an understanding of, some I don't and may never, but it's really fascinating to think through. What I can tell you from a fluidic standpoint is, although our peak velocities are, say, 3 times our average. So if we're at 3 liters a minute, our peak velocities are 9 liters a minute, which is a lot. But what's interesting is when you really dig in and you talk with the fluidics folks and CFD and computational fluid dynamics, turbulent flow takes a while to develop. It can't develop fast enough per stroke. So even though we hit those peak velocities, it doesn't fully develop. It may be unsteady flow, but you don't have those destructive turbulent vortices that can really shear and for the formed elements of blood. I mean, blood is a particulate suspension, right? You know, and particularly the red cells, that they can stretch and deform, and they're made to a little bit. But if they see too much, then, you know, they could be damaged, partially broken down, or completely torn apart, you know, for hemolysis. But, you know, pulsatile flow, even though our peak velocities are higher, because it resets every beat, it can't develop into full turbulence, and that it's full turbulence. That's the problem. And I'll just use another engineering analogy, if you will, again, for particulate suspension, and coming back to thromboresistance and platelets and where they sit and when they get activated. Again, the body's biology, including those formed elements, have been seeing pulsatile flow forever. Continuous flow, if you think about, you know, a rock in a stream, that's where the sandbar grows behind the rock, because the sand that gets washed downstream, then it goes in those little eddies, and then and as the velocity slows down, the sand particles drop and you build a sandbar. What's neat about pulsatile flow, and again, this is from our creator or whatever, the celestial committee, nature, mother nature, whatever your beliefs are, that when the flow stops and then starts again, it clears the downstream particles out. So you can't build a sandbar with pulsatile flow. And so there's many attributes around that at first are counterintuitive, maybe because the peak velocities are so much higher, but the details of what happens to the elements and the elements' ability to temporarily manage to be exposed to those higher velocities, and then they have a reset time. And so, you know, like a lot of, you know, holding a weight out, you can only hold it for so long, but you can do lots of cycles if your muscle has a little bit of a break in between. And that pulsatility, there's so many things that are analogous to that the reason we have continuous flow is it's easier engineering wise. And if you have rotary motors, it's easier to figure out you don't have to create a motor. You didn't before there was Bose, before, you know, there's lots of rotary motors. And so you could build stuff off of that. And it's interesting when you study the histories in the 50s and the 60s, many, many people were very convinced that you really needed pulsatile flow, and they're doing lots of exotic things to do that. But the elastomers of the day couldn't withstand the forces for pushing and pulling at the same cycles and the same stresses that really were required. And so they borrowed pumps from the food processing industry, the roller pumps. And what was neat about that is, from a manufacturing perspective, you could make an extrusion, thick-walled tubing that had extraordinary ability to not have pinholes in it, and you could sterilize it, and you could do that fairly cheaply. And so that's what they did in the food processing industry, and they just leveraged it into blood flow. And then centrifugal came along because, hey, we have these pool pumps, we have these other big turbines. Let's shrink it down and let's get a little bit more hemocompatible. You think about the Medtronic BP80 and the constrained vortex pumps and the cones and how that worked to manage the blood. But that was really because they were more reliable, cheaper to make, more sterilizable. You didn't have ruptures. You didn't kill patients quickly, but it's not because it was more physiologically relevant.
It almost brings me my next question to perusing your website. You talk about how pulsatile flow can help with gut ischemia, AKI. And it's always interesting because you have, similar to the HeartMate 3, which is laminar flow, right? And that's a pretty expensive device on the market. So I think we finally, on one side, we finally reached a point, I think, in cardiac surgery where we're proving to the general population that investing in higher grade technology and, more expensive devices can also yield to a lot more years added to somebody's life outside of a hospital setting. And on the other side of that would be to say that a HeartMate 3 is a laminar device. And one of their major issues is that patients end up getting readmitted to the ICU for, gut hemorrhaging. And you have to, I'm not here saying that it's exactly because it's laminar flow, but it would be interesting to see on those longer term patients if a truly pulsatile device could maybe decrease that occurrence rate.
Yeah. So you brought up a number of key things there. So let me try to address them first. It's important to understand that even quote unquote continuous flow LVADs, say a HeartMate 2 or a HeartMate 3, that they are pressure sensitive devices to varying degree, the HeartMate 3 especially. And so even if you turn them up, meaning they draw out of the ventricle and then return to the ascending aorta, even if you turn them up so that the aortic valve stops opening, there is still some degree of pulsatility because the ventricle is changing its size, and that change in pressure, even if it's not enough to pop open the aortic valve, that gets reflected through the pump. So there's always some degree of pulsatility. And if a patient goes up the stairs, that in the body responds and essentially calls for, more, has greater metabolic demand, that the heart rate increases, and that the aortic valve can open as those pumps work in parallel. Now, and this has been some interesting discussion with, you talk to Jack Copeland and he's an amazing fellow. But let me talk about someone I think has been associated with continuous flow, and that's Dr. Bud Frazier. But if you look at some of his papers 15 and 10 years ago, and I've talked to Dr. Frazier about this, he was very clear at how you set continuous flow parameters is you want to turn it down to keep some of the aortic valve opening, not only because you wanted some washout in the left ventricle and for those leaflets, but also a degree of pulsatility, and that was the art. And, I remember, I think it was a 2019 aside when Dr. Frazier got up and was reminding the room that the whole goal of continuous flow LVADs was to restore native starling-like behavior to the left ventricle. So as the ventricle recovers, even if it doesn't recover enough to take over always the full load, you get back that Starling-like behavior of relax and deliver to get that aortic valve opening. And so what does that mean? That means pulsatility. And so even though it's a continuous flow device, quote unquote, those that have the fewest number of strokes and gut bleeds have been shown to have the greatest degree of pulsatility, residual pulsatility in them. And it is a whole set of studies around that. And so it's fascinating. You talk to Jack Copeland, and he's quick to remind that particularly the gut, parts of the gut, the capillary beds in there are farther away than your toenails. Yet, they're very distal. And when you think about the function of the gut, which is to contain flesh-eating juices that has high metabolic demand to restore those cells that line the gut, it takes a lot of blood and nutrients to do that. And if they're being starved, lots of bad things can happen. And there's a whole series of papers that are coming out on pancreatic proteases that are leaking back into the circulation through not properly perfused gut, and that they in turn can cause vasoplegia, that they can, digest, parts of the circulation that we're helping to maintain vasomotor control. Now, there's still lots that have to be done, but all of that is interesting. And it looks like septic shock that they can't find any root cause for. But if you test for some of these pancreatic proteases, they're now in the blood where they should only be in the gut. So there's a lot there. I know I went through a lot, at least my understanding. Again, I am not trained as a clinician, but I've applied the engineering mindset to 30 plus years of, from dialysis, the laparoscopic, the hysteroscopic, the, circulation to try to understand how the body is reacting both positively and negatively to things that we can either add to mechanically or take from mechanically the body. And it's, and what I'm giving you, whether it's time will bear out how correct it is, but I'm giving you my best mental model, my best understanding why, quote unquote, continuous flow LVADs work, and they work better if there's more pulsatility and more left ventricular recovery. And that's an important piece of them.
This is so interesting to hear just, an overview or kind of revisiting the downstream effects of continuous flow. Cause there have been so many different courses I took, undergrad and grad school that this, kind of makes me think, I feel like I learned something, along the lines of, what you're speaking of, but it's just amazing what this technology can potentially do for our field. And I do have to ask, how did you get involved in this project with Jack Copeland? How did all that kind of evolve? I'm curious.
Well, so I promised myself I wasn't going to go too deep on any of this stuff, and we see how well that worked out. But I will tell you a funny story of how I met Dr. Copeland. And this is also what I'll call the lumpy life of a cash-starved medtech entrepreneur. So we had done some of our the state of New Hampshire we signed up in 2010, I think, for a state of New Hampshire grant. We won it working with some great folks up at Dartmouth. We did some of our first animals, and that was great, but it was a matching grant, and we basically killed ourselves, meaning the business, to do our matching part. I was pretty desperate in 2013, and I went to a pediatric conference in Hershey, Pennsylvania. My wife was kind enough to put me in the car with what prototypes I had and the credit card, and went down there just kind of really just saying, if I don't find any traction down here, I think I'm going to have to go get a job. And she's like, yeah, I remember we used to have two incomes. That was nice, dear. So anyway, went down. Maybe the second day of the conference, a doctor from Turkey got up, and, she had very good English, but I was working hard to really understand all that she was saying. And she talked about doing pulsatile flow with kids and CPB using a roller pump. So speeding up and slowing down the roller head. And I couldn't quite tell, but I thought it was generally positive. So I was kind of excited about that. And the fellow sitting next to me got up and asked a question at the end. And he said, so let me just be clear. Were the outcomes better or worse when you used pulsatile CPB? She said, oh, absolutely better. These kids did much better. He said, okay, thank you. And he went and sat down. And I thought, I'm going to talk to this guy. So after the session was over, I introduced myself. I had a little brochure and I'm chatting. And he's like, what? I didn't know anybody was working on pulsatile flow for, real pulsatile flow for CPB. We chatted a little bit more and he said, so what are you doing here? Do you have a booth? And I said, oh, no, we couldn't afford a booth. It was $10,000 or whatever it was. I said, so I said, I couldn't afford that. I said, but we are trying to see if we can find a clinical champion, somebody that would, help us on both understand what we've created, but also, help us take it out to the world and, maybe, get some excitement. He said, that sounds like a great idea. And I said, so if you know of anybody, I'd love to know who. He says, I do. I said, well, great. Who? He's like, me. And I said, oh, great. And he said, look, but do you have a prototype here? And I said, I do. But again, we couldn't afford the booth. And so it's in my room. It's my hotel room. He's like, great. He said, I have a session to go to next. He said, but maybe after that, we could go check out what you got in your hotel room. I said, sure. And he said, hey, I said, what session are you going to? So I'm going to, it's on Syncardia. It's a wet lab on Syncardia. And I said, oh, fantastic. I'd signed up for that session too. And he's like, do you know where it is? I said, I do. He said, well, let's go. So off we walk and we get to the door and the room's full. And he and I are chatting some more at the door and, what do we do? No. And finally, this lady comes over and says, we'd like to start the section. I said, I'm sorry. I apologize. I just got caught up talking. And so I go and sit down. He goes up to the front of the room. He's giving the wet lab. So that was Jack Copeland.
He was actually, so I worked with him when I was a student. So this was like almost 13 years ago. I attended the University of Arizona for Perfusion school, and he was one of the physicians or surgeons that I trained under for 2 years. He was a very interesting guy. And University of Tucson, Tucson has or holds the headquarters for Total Artificial Hearts and Cardia. So it was really interesting learning from him. He's obviously very passionate about what he does. And I think that's great. It sounds like it was destiny on your part to meet him.
Well, it was a defining moment for us. And, he's helped us a great deal, since. And after that session, he did come back to my hotel room and, kicked my socks underneath the desk and showed him the prototypes. And he helped write a grant. We didn't win it, but he helped write a grant for the American Heart Association. But anyway, that led to some angel funding for us and really got us going on the angel funding side of thing, which was critical. So that, forever that moment was a pivotal moment and Jack Copeland was right there.
Wow. Congratulations. What a partnership.
Thank you. No, very lucky. And I'm embarrassed. I heard the name kind of, but not enough to be in the moment and recognize who I was sitting next to and talking to until I was pretty embarrassed when, sort of figured it out, but he was fine with it. He was great, gentleman.
That reminds me of how I met Mel. And that's how we started this podcast. So.
Well, yeah, I mean, I actually saw this device for the first time at AMSEC 2 years ago. They did a Shark Tank and you were on it. So you've been quite a prominent Shark Tank contributor.
Yeah. Believe it or not, although sometimes it feels like 2 years ago, it was just last March. It was just about a year ago.
Yeah. It was a year ago, right? Yeah. Okay. And I was blown away by some of the components on the device and how attuned it was to perfusion from, the end user experience. Like as a perfusionist, like the first things you're always looking at are, okay, like what is the backup hand crank look like on a device? Or, is there a built-in battery or, is there a backflow prevention? And so those are kind of like the scary things that we look at. And I was really impressed with your device. Like the hand crank on it is super easy to use. The design of the pump itself, like just the science behind the tech allows for it to not really develop a lot of air very quickly. And if it does, it pushes it to the top of the device. Like if you want to go through a few of those components, I'm sure you could probably describe it a lot better than I am.
Well, thank you for bringing that up. And so architecturally, how the basic elements work, as I mentioned, have been there for a long time. But we've worked with some great perfusionists too. Pat Grady, Cleveland Clinic, had been part of, dozen plus animal experiments, and his team there. Ellen O'Brien, who I'd first met at AbbeyMed years ago, she worked very closely with us. Kevin Cotter, that he really, they spent a lot of time helping us understand beyond the basic elements of the orientation for air and level and bubble and pressure. And then as we collectively developed the hand crank, the hand lever, and how that all worked out. And so it was, again, so many of those things. We had the basic ideas to start, but just worked with a tremendous team and passionate. And, Kevin Cotter's a great guy that is, been doing perfusion for, since the 70s, early 70s, and all the things that he's seen. And he just brings it with just affable wisdom to try. So we can get that kind of a reaction, Mel. And it feels good to hear that, from card carrying perfusionists. But a lot of time, again, thousands and thousands of hours of engineering and understanding and argument and mistakes went into that so that we could, our goal has been to, really, I don't know if the right way to say it is to delight the perfusionists so that they can get back to managing what they need to and not get distracted by the differences of VentriFlo, but can be quickly familiar enough with the differences that they can then begin to exploit that. And so, some of, the work that we've done with ex vivo hearts at Mass General and the team there, including really some great perfusionists that, again, most perfusionists see a third way and they're like, yeah, right. But as they spend time, then they can quickly acclimate to it. And then collectively, with Joe Catricala and Nate Minnie and Allison Pitty and Kenny Shan's team at Mass General, what we've been able to do for the ex vivo heart to counterpulse and basically take better care of the heart in the box, which of course is what our goal is to do for the heart in the body. And really by counterpulsing, we deliver our stroke volume against a closed aortic valve to promote superior coronary perfusion. And that in turn has allowed us to shift and have a working mode, not just a Langendorf mode on the heart. And so once you get the working mode, which is not able to be done today on the commercially available devices, then you can start to really assess performance. And that's something that with the VentriFlo counterpulsing from the ECG signal, you can do.
Yeah, I actually knew that I knew you worked with the perfusionists at MGH. I know Joe and Nate for a couple of years now, and I was always so jealous, like watching their videos of them getting to use this device before it gets on the market and, test it out on ex vivo experiments. And it's honestly, it's really interesting too from an industry perspective, because getting that hands-on experience with the pump, even if it isn't on the market yet, but it allows you to have inroads as well with, at your center to let people know that there's a potential device that could be hitting the market soon that could help with, certain patient populations, or just seeing how the organ reacts to the device firsthand. You can kind of start to look at your patient populations and start to pick and choose and say, we had a patient last week and that patient probably could have benefited from something like this, but it's not available yet. So it almost gets your gears running in terms of quality improvement in clinical practice. So by the time the device does hit the market, you know who to target, which can be important too, I think.
Yeah, no, I certainly agree with that. I mean, this stuff doesn't happen without collaboration at all stages and in both directions, if that makes sense, from academia to industry to academia, with the clinical piece in there. so that it maintains relevance. That, again, the greatest invention in the world. And one thing that I can't even tell you how incredibly frustrated I am. We have this amazing device and we have yet to help a single patient, and it's driving me nuts. We're fundraising dependent, and it turns out I may be lots of things, but I am neither a natural nor gifted fundraiser. And we've got to crack that so we can, we're $2 million away from an FDA submission.
Wow.
We need to finish that up to get that in the hands, and then absolutely finish what we've started at Mass General, at Cleveland, Dartmouth, other places that at Brisbane, Dr. Bartlett's lab in Ann Arbor, that, to get this to help patients and stop research use only kind of systems. Although I'm thankful we have one, I'm glad we could do it. We really want to get out there to full support for this size system for pediatric, but of course, partial support, because one of the things that, having studied this now for a couple of decades or more, it's so clear to me. If you can augment what the weakened left ventricle is doing in the right way, what matters is combined flow of 5 liters a minute, not flow through a device at 5 liters a minute. And when you think about what current VA ECMO is, as potentially life-saving as it is for these cardiogenic shock patients, whether AMI or heart failure, the more you turn that up, the more you're beating up the left ventricle and holding that aortic valve closed. And frankly, from an engineering perspective, dumb as a rock. It's the last thing you want to do. What you want to do is only deliver against that closed aortic valve and drive oxygen, nutrient-rich blood into those coronaries. And then when the heart goes to eject, you want to have it eject into a falling pressure. And that's what counterpulsed VA ECMO does. And with a true volumetric delivery and strategically timing when that volume hits the elastic arterial tree, and ensure that we're just pushing against the closed aortic valve and not when it's open in the struggling left ventricle. And, we think that's going to change really so much of what happens in VA ECMO for decades. It's been a 40-50% mortality. And, today people to vent the left ventricle do some pretty exotic things, right? And so in our case for counterpulse VA ECMO with VentriFlo, what the benchtop is shown and we're moving into animals is to show that we can take better care by augmenting the weakened left ventricle pulse and basically alternating between the ventricle delivering and VentriFlo delivering, ventricle delivering and VentriFlo delivering. So the elastic arterial tree sees 2 pulses. You don't have to worry about poor washout in the left ventricle, and you can tune where you get that oxygen nutrient rich blood depending on how you splice into the elastic arterial tree. So we're very excited about that. We think that's very important. And again, at the high level, our goal is to save lives. And because there's a new option of AA ECMO, and I'll talk about that in a second, because we're very excited about this. VV ECMO and VA ECMO. We're talking about that there may be an opportunity to get that benefit with just a single site into the elastic arterial tree. So with AA ECMO, and you can only do that with a true volumetric displacement device like VentriFlo. So it essentially functions like an intra-aortic balloon pump, but it moves volume in the blood volume, not helium in a balloon. So imagine coming into the bottom of the descending aorta that we draw out from up to 40 cc's from the elastic arterial tree ahead of when the left ventricle ejects. And so essentially the left ventricle is ejecting and we're filling VentriFlo at the same time. So what the left ventricle sees is almost a constant pressure. And so we can get a better stroke volume out of the left ventricle because it's not getting higher and higher, because we're, while it's delivering, we're filling. And then once the ventricle goes into its diastolic recovery, then we deliver, but we deliver more vigorously than the left ventricle could. And so then it's like a mechanical inotropy. And we deliver that back into the elastic arterial tree. You get all the benefits of that pulse, including feeding those coronaries. And what the benchtop testing has shown us is that we get the same or even a little better stroke volume, depending on the timing. And we get improved coronary perfusion somewhere in the order of 10 to 20% in terms of the reduction of wall stress to stroke volume ratio with AA ECMO. And so we're very excited, about that. And if you have a patient that is, starting to desaturate, they're at 90 or 85% their arterial saturation, you put them on AA ECMO, you can get it right back up there. Same time, you're doing what you're supposed to do for these cardiogenic shock patients, and that's rest the heart to recover it, to allow it to recover.
It makes so much physiologic sense. I mean, I've been doing perfusion for so long and I feel like I've been doing it wrong.
No. Well, look, Tiff, you can only work with the tools that are, cleared for, that's, you've got what you've got, right?
Right.
And if people say, well, and I will tell you, different check writers over time have said, geez, this doesn't look that complicated, Doug. Well, I'm telling you it is. But anyway, they say it doesn't look that complicated. And then they say, well, so because it doesn't look like complicated, anybody should have been able to come up with this whenever they wanted to. And if it was really important, they would have already done it. And the answer is it's incredibly hard to manage and control simply and safely the right pulse because you have to be highly responsive. And that's what we get because we're not a pneumatic system. You have to be pressure sensitive, right? So if you clamp off an inlet line or you clamp off an outlet line, we just stop. Why? Because we're coupled to the blood. And you have to be volume displacement. Otherwise than that, you're not getting that ability to deliver through an oxygenator and a cannula that volume into the elastic arterial tree to let it do its work. And you have to put it in a package that can allow you to be ECG sync. And these are all things that are, each one conceptually is fairly straightforward, but it's very hard to do for variable stroke volume. So if you look at the Berlin heart, for example, they have many different sizes because those valves only work and the chambers only work with proper washout. So they're filled to empty. We are not. And it's because of the ball valve architecture that if you think about, for instance, what a tri-leaflet valve is, a tri-leaflet valve is really three valves. There's three leaflets that have to open, and they open. If you study it under slow motion video, they open in sequence. There's always a little bit weaker, then a little bit stronger, and then the strongest leaflet that opens last. If you don't have a full stroke volume, that third leaflet never opens, and therefore behind it, it never gets washed. And that's where hamburger starts to grow. Again, colloquially speaking. So, but a ball valve, whether you've got a little stroke volume or big stroke volume, that ball goes through its excursion. It turns, it twists, there's flow all the way around. And unlike a Starr-Edwards ball valve, which, by the way, there are still some people walking around with a Starr-Edwards valve 50 years later. But a Starr-Edwards valve, there's a cage that goes around it. So there's permanent stasis spot behind that cage. But we control that conduit that it sits in. And so we don't have a cage. We have fins that are tuned to match the flow that goes over and then comes back for that good washing, not only of the valve, but of the whole conduit that ball sits in a way that you just can't do with any other kind of valve. And then when the ball valve seals, it seals completely. There's no jetting that can cause hemolysis. When it's off, it's off. And you can only do that with that architecture. So the variable stroke volume that's highly responsive because it's a speaker. You can hear it in your ear how responsive the speaker is. But essentially that's what we have now coupled to the blood. And because it's coupled, if you clamp the inlet, our diaphragm can't fill. So it's at the top of the chamber. And then you release it and it'll fill. if you clamp the outlet, it's at the bottom of the chamber. It can't deliver because it can't deliver past, but we're only putting in so much energy into that speaker. And just like you can put your hand on a speaker and stop it, that's what that pressure does. And that's where, yes, it's a blood pump, but really it's also a blood transducer because of that coupling of the blood to the diaphragm.
And you may have already kind of touched on this, but how much is this device auto-regulated versus something that you would have to adjust manually to maintain a certain pressure or whatnot?
Well, so let's talk not ECG sync for a moment. So how we have it set up, if you turn it on, it comes up naturally at 70 beats a minute. And our stroke volume, our stroke strength is set to 0. And so then when you start turning that knob up, you can go up to 100%. You're like, what is 100%? It's just like your radio, right? Speaker, you turn it up. You're putting power into that at 70 beats a minute. So if it can fill, how much it can fill in the time that it's allotted, and so I'll make it simple. Let's say it's 60 beats a minute, and we're not quite 50-50, but just for easy math, it fills for a half second or tries to fill for a half second, and however much it can get in a half second, and then it delivers for a half second. And if you want more, you can turn up the volume. You want it louder, you turn up the volume. And so we have a flow meter that's on the outlet line that's also an integrated bubble sensor. And you can set it up to alarm and stop, to alarm, or to just ignore it. But you always get your flow. And so then you can look at your pressure and you can adjust that knob based on what you're seeing and what you're striving for to try to get the flow rate that you want. And if you say, and some of the things that we've begun to explore with Dr. Fukamachi and the team at Cleveland and Pat Grady is that in general, it looks like lower beat rate, larger stroke volume is generally better than the opposite. But there's still, literally, because this tool has never been given to you, to them, there's so much left to do to explore the hows and the whys and the whatnots around that. So today, it's you, just like you do today, you turn that knob and it fills and delivers. You check your reservoir if it's in a CPB setup, and because again, you can't deliver what you don't fill. And then you hopefully have selected the right size cannula and oxygenator, and for the circuit to achieve your flows. Now in the future, could you imagine something more closed loop? Yes. Could you imagine it more integrated with a full system? Yes, that's all in time, but we've really tried to make this a standalone arterial, circulation pump with integrated, level, bubble, pressure sensors. Now, all that said, because it is this speaker-based technology, it is inherently pressure sensitive and it adjusts beat to beat. So if you clamp off your outflow, you'll see your flow drop. We'll put up a low flow alarm, depending on where you've set that alarm. But nothing bad happens, right? You don't blow a line or anything like that. So that the system exhibits Starling-like preload and afterload sensitivity in a good way, but you wouldn't want to, there's no reason that you would sit there with a clamped line and try to, you would turn your stroke strength down. You wouldn't want, there's no reason to sit there, but you got to solve the problem why you're not getting flow. And by the way, in that same scenario, without a reservoir in ECMO, one of the things that we've seen and we saw with Dr. Bartlett that because we're only periodically drawing from the inlet, you don't permanently collapse anything around that cannula, right? Because basically you're only drawing half the time and the other part of the time you're delivering. So you're always going back and forth, and it's a different way to think. It's literally two pumps that function collectively together. I'll give you another example again with Dr. Bartlett. When we first went on the placement of those cannulas, we did it with the manual driver because you can feel how well positioned the inflow is by how hard it is to lift up on the handle. and delivering. So we repositioned rotationally and the amount of insertion till we felt that the cannula was in the optimum spot for drawing, for drawing from drainage from the animal.
So I have a little bit of a visual forming, but just to paint a little bit more of a picture, you made a comparison earlier to Berlin heart, and I couldn't help but notice just checking out your website, VentriFlo.com. It looks a tiny bit like the Berlin heart, but can you tell us like how large is this pump? How small is it? How much does it weigh?
Yeah, so it's a 2.6 inch diameter diaphragm. Weighs about a third of a Coke can. To calibrate you. This size has 3/8 inch fittings. So in the architecture of having the inlet and the outlet, really in the same orientation, really like a roller pump or like a Berlin heart, allows us to manage that flow well, and what sets up what we call the fluidic flywheel. So even when it's a small stroke volume, you never stop movement in the chamber. It speeds up and slows down depending on where you are in the fill and delivery cycle, but you're always getting movement in that chamber as that fluidic flywheel speeds up. And this is, in the orientation and the dome shape, that's why air will accumulate up at the top, because it wants to come into the center as the fluid goes out, managed purely by that, the rotational inertia of the mass of the blood. But so that was just a nice architecture. When you think about this sitting on a cart, the same way a roller pump would, with the inlet and the outlet kind of facing. I know many things have gone mass mounted now, but that was where we wanted to start as just a basic principle, and then to be managed if it was a standalone in an ECMO, on an ECMO cart.
I'm kind of dying to ask. I know like certain pumps and devices have like a hand crank, if there's a device failure. Is there anything like that for the VentriFlo pump?
Yeah. So what we've got set up is that, this slides into what we call the horseshoe, and it couples to the diaphragm, mechanically couples to a T-stem. And so then it becomes one with the speaker, so we can push and pull. If everything went away, you can slide that out. You turn it over in what we call turtle mode. You slide it back in the horseshoe, and on the side of the device is just the nifty little handle that you take out and you snap it in, and it's just a lever. And allows you to just quickly, in less than a couple of seconds, to be on manual pump. Now, if for some reason you didn't even have that, you can still pump by hand. It's harder to fill without the lever, and your thumbs will get tired pushing. But if you drop it down low so you get gravity on your side, because of the one-way architecture of both the inflow and the outflow valve, you can only have net forward flow, and you can essentially do like CPR with the pump itself. And that's something you can't do with a roller pump and you can't do with a centrifugal pump, but you can use this just in the palm of your hand.
Wow. Pretty cool.
Well, I don't know if Tiff has any other questions or if there's anything else that you wanted to add to that maybe we might have missed during our discussion.
Well, let me apologize to you and to any potential listeners that I was going to try not to get too much into the details, but I get so excited about this, and I've been studying it for so long, and I think it's so important. Our tagline is blood flow the way it should be. And that's not an accident, right? As we started to think about what really are we trying to do, it's really restore blood flow, the way it was from the womb on up. And as simple as that is, we think it's a powerful concept that can really evolve and change, and I think open up possibilities that haven't been there, particularly, for instance, with these cardiogenic shock patients. I mean, one of the reasons I think outcomes have not improved is continuous flow. The more you turn up in VA ECMO, the more you're fighting the left ventricle versus augmenting with a reciprocal pulse, if you will. So that's blood flow the way it should be. And we think there's so much more to explore. And what we've seen always with perfusionists is, you can only work with the tools you've had and you've been trained with. And, it's an intense job, right? I mean, I'm not telling you guys anything you don't literally live every day, but I vision it like a pilot. Yes, you may have taken off and landed 1,000 times, but every time, still got to pay attention, because things can happen and they do, and you have to be prepared to respond. You hope they don't happen. And the reason I go into all of that is the nature then of that is to be skeptical of anything new. And you don't have a lot of practice it's not like there's 10 other kinds of pumps that you've been handed and have learned. And that so VentriFlo is a third way, is something new. And so we're asking for a little bit different part of the brain initially, to be awakened or to be utilized. And then our goal is to partner, with the community to bring this out there in a safe and, a positive way to learn a new tool and to learn everybody can see VentriFlo is different. The question is how, where, when, and why do we exploit those differences for patient benefit? And we have obviously great ideas of where we think that is, but collectively we'll all have to work together to demonstrate that. And it's both exciting and frustrating because it hasn't happened yet. So I think that's really, an important point that I'd be remiss to say. And then lastly, in maybe not even lastly, but importantly, all of this takes money. None of this that we've talked about and none of what the team over time has been able to accomplish with VentriFlo would be possible without some angel investors. And we're solely funded by angels. Just incredible people. Our main angels, I can't thank them enough for what they have done and led the way for dozens of other angels. And these are people that, have chosen to believe and written checks and given it to me to spend on this, to try to create this new tool. I mean, think about that. What, trust that is in an idea, in an individual, in a company to do that. We've raised $17 million, all from angels. And, like I said, we're $2 million we feel from, getting to that 510K submission. I'm frustrated that I wasn't able to do it with what we had. I'm thankful that we've accomplished the great things that we have in these last couple of years. The collaboration with Mass General and so forth has really revealed a lot. But it's only going to matter once we get on the patients and can really start to make a difference in their lives and improve clinicians' ability to help these patients. I have to make a shameless plug for anybody that happens to listen to this to recognize that, we've come a long way. We're not done yet, and we can only go as fast as the next check.
I'm very inspired by your passion behind this project. It sounds like there's been a lot of strong forces behind you, and you have been a strong force in keeping your head down. And I can imagine the countless hours, you've spent on this project and years, mind you. But, this is so relevant to the field of perfusion. And we're clinicians first, but we're also kind of wannabe engineers to some degree. We sit behind the pump and we can't help but wonder how certain things work and, the just how to see the engineering mind behind it. So we really appreciate everything that you do. We wouldn't have a job without the intelligent engineers like you. And this is just, in my mind, it feels very revolutionary. I mean, it's very physiologic and very exciting to hear that this is happening in the background, and I can't wait to see it in human models. So congratulations on all your work.
Well, thank you. And just to be clear, I'm a wannabe clinician. So, I mean, I think that's really where the collaboration, works, because the point is, it is at that interface to try to solve these problems. And what I would say is, although people can look at our system and it's a compliment in some way, they say, well, that's not that complicated. Hey, we worked really hard at it, But the other side is, I believe this. I don't know what the right number is, 5 years from now, 10 years from now. There'll be a point in time where we look back at continuous flow and it's, well, that's the tool we had at the time. Thank goodness we kept going. Thank goodness we didn't stop there. Thank goodness we decided 70% solution wasn't good enough for, because we have to get better at the amount of kidney failure and gut issues and arrhythmia and brain issues with CPB patients. We have to improve the mortality for cardiogenic shock patients. We need systems that can evaluate hearts on a bench before they go in for transplant that are truly loaded, so we can take hearts from farther and that are more questionable and evaluate them before the surgeons, really commit to the final piece, the AA ECMO. And that's a whole new, you can't do that with a roller pump or a centrifugal pump because you can't strategically remove a whole stroke volume and then bring it back to the system when you want it and how you want it. All of those things put together, we'll look back someday in the future and say, yeah, we did, we had tube crushers and we had, pool pumps, but, thankfully there's a better way. And that's the way it is in medicine, right? And like a lot of things, it's dose and delivery dependent. And now that we understand what is the right dose and the right delivery and continue to explore and exploit that, you won't go back to the wrong dose and the wrong delivery, and that'll be fun. I just want that to happen. I'd love it to happen in a year. But it's it takes a lot to overcome that. We started maybe, I think before we were recording about, clinicians appropriately are trained as essentially historians. They're trained how to do it with what's already been done. But innovation, by definition, is doing something new. And anytime you're doing something new, it doesn't always work out, that there's risk to it. And it's a different mindset. But, when I hop on a plane, I'm not looking for that pilot to try something new, right? And so where you figure that out, how you blend that together of trying something new, when to try something new and how you move that along. That's what's happening now. It's very fun. It's very exciting. And again, other than the money part, it's been a fantastic journey. But, that's the piece that is so critical. And we need that to finish this job to help the patients. We deeply believe this is going to help.
Yeah, it's something that's kind of embedded in our culture in medicine, at least since I've been a perfusionist. A lot of people or a lot of perfusionists I know say, well, that's just always the way I've done it. We're not going to change it now. Why break why fix something that's not broken? So I think there's a lot of those hurdles to get over, but I can't imagine the feat of, making it from animal to human studies. And yeah, I applaud you on all your work, and I'm just really excited and excited to look into my future as a perfusionist and hopefully, not say those things to the people that I mentor. I want to try new things. I want to change. I want to be better. So we have this on recording, so I have no choice.
Yeah, but it's great. It's great you guys are doing this. I really appreciate the invitation. I hope you've enjoyed our time together. And I really hope the folks that choose to listen and enjoy it. And please reach out to me anytime, Doug Vincent at VentriFlo.com. If it isn't clear, I am happy to talk about this to anybody in any capacity, and especially if they have a checkbook. That'd be fun.
That was a great way to end the episode. Thank you, Doug. This has been such a long-awaited episode, and we really appreciate your patience again with us.
Yeah.
Because we really wanted it, and you're finally here, and we've learned so much from you. So thank you.
Yeah,
thank you. Thank you. I really appreciate the time.
That's a wrap for this episode, your source for all things perfusion. If you have any questions, comments, or topics you'd like us to cover, please send us an email at pumpcasters, @gmail.com. Until next time, keep the blood flowing and an eye on your level. From the latest techniques to the biggest challenges and trends, we cover it all on Pump, the perfusion podcast that never misses a beat.